Hello and welcome to our webinar, Detect Wire and Component Tolerance Violations and Lower Product Costs. My name is Hans-Peter Bleyer. I'm Pre-Sales Engineer of Zuken and I will do the webinar together with you. Here is the agenda for our webinar today. First, we want to find out what's the problem, why you should care, and what you will learn today. Next, you will get a solution overview, and then I will demonstrate the solution with some live examples. So, first of all, what's the problem? The lack of proper design analysis is leading often to an under-engineering with very small operating margins and mostly a low quality. On the other side, this could lead to an over-engineering with excessive design margins and very high complexity and also costs. So the goal should be right engineering with a safe and optimal operation of the whole schematic. Why should you care? Under-engineering involves risks such as liability for fire or injury and costly product recalls, and also field failures and costly repairs. Over-engineering may lead to unnecessary costs, weight, and complexity. And here is what you will learn during this webinar. The benefits of integrating electrical checking into your design process, how to check voltage and current for all components in your design, methods of optimizing wire gauges to save weight and costs, analyze the design and check the internal resistance of connectors, and how to ensure your design operates within the loads permitted. The solution for your problems is E3.eCheck. E3.eCheck takes away all your headaches and makes life easier for you. E3.eCheck is part of the E3 series eCAD software solution from Zuken, a software which was designed for electrical wiring, control systems, and fluid engineering. Let's go on and have a closer look to E3.eCheck. E3.eCheck is no simulation. There are no time-dependent functions at this time, as well as no functionality for non-linear components. And presently we have DC functionality, but no AC functionality. The goal of developing E3.eCheck was enhancement to the already existing very extensive online tests, optimized support for the design engineer, simple operation, an easy-to-use tool, and a minimum amount of time to enhance the library. E3.eCheck gives the design engineer current information about the following topics. How much power do we need? Is the power supply sufficient? Are the operating values adhered to minimum voltage, maximum permitted voltage, maximum permitted current, and maximum permitted power? Are the cross-sections sufficiently dimensioned? Are the fuses adequately dimensioned? What effect does the internal resistance of connectors have? What is the maximum voltage and current in the schematic? And what is the effect of changing the status or the position of switches? To get some impressions about E3.eCheck, we will have a look at the first example. Here we have a small schematic showing some basic functions of E3.eCheck. There is a voltage supply with 13 volts. Next we have a fuse with 10 amperes, a stepping switch with 4 positions. Position 1 is active. A lamp -P12 with a 5 watt load. Symbol is yellow, means status is active. Here we see an ampere meter showing the actual current, which is 0.45 ampere. A voltmeter shows the voltage, 13 volts. For the symbols, there are additional text notes available to show the actual voltage and actual current. And when you position the cursor over a symbol, you can get an enhanced tooltip with additional information about the selected symbol. You will see the actual voltage and actual current for each pin of the symbol and status information regarding whether the check passed or not. Additional information is also displayed in the result window. Next, stepping switch S21 is set to position 4. That means lamp -P15 is now active, lamp -P12 is no longer active, and because lamp -P15 has 60 watts, there is a current which has increased to 5.39 amperes. Now we have switch S22 closed. As a result of closing S22, fuse F10 has blown, shown in red color. Lamps -P15 and -P16 are not active anymore. Because fuse F10 has blown, there is a break and therefore we have no current. And in the result window there is an error message showing the reason why fuse F10 has blown. There was a current of 10.744 ampere, and that's too much for a 10 ampere fuse. Here we have a second example. In this example, switch S20 is open at the moment. Connected to the switch is a relay which is not active at the moment. The contacts of the relay, normally openers, are open, and so the lamps connected to the contacts of the relay are also not active. Now we have closed switch S20. Now we have closed S20. That means relay K20. Switch S20 is closed now. Relay K20 is active now, and the contacts 1314 and 4344 are closed because the relay is active. That means the lamps connected to the contacts are also active, and there is a message in the result window about the active state of the relay. The following functions are available: specific settings in the project parameters, enhanced tooltips for symbols and connections, result of calculations displayed in different colors, output of actual status, warnings and error messages, a E3.eCheck toolbar and also additional items in the context menu, additional graphic to show the state of switches and relays. E3.eCheck covers symbol and component-oriented work. A component can have multiple symbols, for example a relay or a switch with multiple contacts. There are standard parameters for connections like wire color, cross-section, wire length and also wire resistance. And it is also possible to use physical cables or wires with their corresponding values. Schematics can have multiple sheets connected via signal cross-references, and also hierarchical design is supported by E3.eCheck. The settings for E3.eCheck are divided into 4 sections. There is a general section, there is a section to define the colors to show the state of the symbols, then there is a section to define the settings for connections, and also a section to define the default settings for special components. You will see this later in the demo. To give you a live demo, we will first create a new project from scratch using E3.eCheck from the beginning. Here you will see some basic functions. In the next step, we open an existing project to show you the different states of symbols. You will see the behavior of different functional units. Then we have a look at the effects of the wire resistance, and also we will see the effects of connect elements. I will show you E3.eCheck with multiple sheets and different hierarchical levels, and at the end we will get some information about voltage and current in the schematic. Now we will see the live demo. To show you some live examples, we have started E3 series, we have a new project, we have an empty page, and before we go on, let's have a look at the settings of E3 series. For the electrical checks, we have 4 sections. Here the general section, we can activate or deactivate the electrical checks. We can activate an acoustic signal on error. We can show the current flow on a selected connection line. And we also can add missing attributes to new net segments. In the next section, we define the default colors for an active load. That means if a lamp is active, the color will change to yellow. And there is also a color for an active coil, for active LED, and a color to show a blown fuse, and also a color to show other errors. Here we have the default values. They were added to new connection lines as attributes. There is a wire length, there is a wire cross section, there is a wire color, a wire weight, and a wire specific resistance, and also an ambient temperature, which is used for the calculations. In the last section, we have values for some special components. For a fuse, we can specify a duration factor, here 70%. This means when the current is more than 70% of the nominal current of the fuse, you will get a warning. There's also a diode voltage drop and internal resistance of connect elements we can specify. This one will be used when there is no resistance for the connector defined in the component database. So far for the settings, and now let's do a small example. Let's start with a power supply, then we need a fuse, next we need an indicating element, and to do the calculations, we need a special symbol, which is the base for the calculation. This is 0 volt, and when I connect this one to my power supply, you see the text node has changed for the voltage. And when I connect the other ones to the fuse and to the lamp, you will see all the text nodes were changing and showing the actual values. The lamp is active now, it's shown in a yellow color. When I hit the lamp with the cursor, you will get an enhanced tooltip with informations for each pin about the actual voltage and actual current, and also information if the check has passed or not. Now let's go on. We want to switch on or off our lamp, so we select a switch in the component database. We place this switch on the connection line, and you see the lamp is active now. We select this switch, and let's move these icons a little bit closer to the switch. That are the icons for the electrical checks. And here I can change the state of the switch. So it's closed now, the lamp is active, and it's open, and it's closed again. And you see the values for current and for voltage, they are changing, they are always actual. Now let's place a second indicating element. We are placing a second lamp, and when you compare it to the first one, you see this one has 5 watt, this one has 55 watt. And now let's see what happens when we connect this one parallel to the first one. And now you see the lamps are not active anymore, and you also see there is a red marked fuse. This shows us the fuse has blown. When we look in the results window, we get the information. The current now would be 5.512 ampere, and that's too much for a 1 ampere fuse, so the fuse has blown. When we go to the tooltip, you see the check was not passed. And now what can we do to solve the problem? We select the fuse, we go to the device properties, and we change the component. So we use a fuse with more ampere. We have a 20 ampere fuse now, and you see everything is working. Our lamps are active. We have a current meanwhile from 5.51 ampere, so it's enough for this fuse, and we should have no problem. So far for this small example. Now let's switch over to another project, a project with some examples. Here we have the representation of different states with E3.eCheck. We have a power supply, a second power supply, serial to the first one. We have some resistors, so we can with the stepping switch we can switch different voltages, and so you can see what happens to the different components. Here we have a lamp. In the moment we have no voltage, we have no current, so let's activate this stepping switch. Now we have a voltage from 12.99 volt and a current from 0.45 ampere. Everything is okay. You see no message in the result window. And now let's go on. Let's activate this switch once more. We see we have 7.67 volt, and that's too low. The voltage is below the minimum voltage of 9 volt. So this is the reason why this lamp is not active. Let's go on. Next step, and you see the color of the lamp has changed, and the reason is the lamp has been broken because the maximum voltage of 15 voltage the maximum voltage of 15 volt was exceeded. Now let's see what happens to a resistor. Here we have a resistor. Let's activate this one. You see we have a voltage, we have a current, everything seems to be okay. Now next step, and you see the color changes, it shows an error, and here you see check passed no, and in the result window we get the information this resistor has a power of 25 watt, but this was exceeded by 33 watt. Though this is the reason why the resistor was damaged. Next example, we have a fuse. Let's activate this one. We have a current of 0.86 ampere. Here you get a message that the fuse duration factor has reached. It's still working, but you have to be careful. And now when we go on, we have blown the fuse. It's shown in red. And the reason is there was a current from 1.294 ampere. That's too much for a 1 ampere fuse. So that's the reason why the fuse was blown. And you see it always actual in your drawing. Next we have a relay, and this relay has multiple symbols. They belong to this component. And now let's see what happens. We are activating the relay. The color for the coil was changing, and also the contacts were operating, and there you can see these gray circles, and they show where there's a change in the color. So let's switch off and on the relay, and you see the changes here. And now let's go 2 steps further, and you see the color changes to error. And what's the reason? We have exceeded the maximum voltage, so the relay is broken. We go 1 step backwards, and you see now I have the voltage from the minimum voltage from 10 volt. It's below, so the relay will not work. And here you can see there's a voltage about 6.16 volt at this relay, so that's the reason why it's not working. Next one, we have illuminated switch, and when we activate this switch, the additional contact operates and also the lamp is active. Let's see the next example. Here we will get some information about the wire resistance. Let's zoom in, and here we have a schematic. We have a lamp which is active, and we have wire lengths. When we select the wire, the connection, you see the current flow, and now we want to change the connection properties. We want to change the wire length to 2000 millimeters, and this causes that our lamp is not active anymore because the voltage is below the minimum of our lamp. So what can we do to solve the problem? Here, for example, we have a physical wire with a square diameter from 1.5 square millimeters. So let's assign this wire to this connection, and you see our lamp works proper and everything is okay. Next, we go on to another example showing the contact resistance. Here we have the same circuit. We have a contact, and we move this contact on the connection line. You see there's a mating part placed also, and you see also the voltage has changed because this has a connect resistance, and we place the next connector on the connection line, and you see here the voltage will change also, and now we are below the minimum voltage. Our lamp won't work. So let's go on to the next example. Here we have some switch elements. We can define a switch in the E3 database, and we can assign a state to the switch. We can switch this on or off, and you will see the result here with this lamp. And the next one is illuminated switch. I switch him on, the lamp is active and the additional contact is working. And when I switch it off, this lamp works because this is a normally closer. Here we have a stepping switch with 4 positions. So you see the result was indicated with the connected lamp, and I can choose one of the 4 positions. Here we have a special switch with 3 positions. Position 1, this lamp is active, and position 2, both lamps are active. So we can specify different switches with different states and can use them for E3.eCheck. Next, we have an example showing some relays. Here, let's make a zoom. This relay is connected via this switch, and when I operate this switch, have a look at this area. Here are the contacts of this relay, and you will see what happens when I activate this switch. The relay coil is active, the contacts were operating, and you see this lamp is deactivated, this is activated, this relay was deactivated, this is active, and these are the contacts of this relay, and when I switch it off, you see the difference again. So you can use multiple relays in your drawings, and it's also possible to do drawings over several sheets using signal cross references and also using hierarchical blocks. So let's give you a small example here also. We make this a little bit smaller, and let's jump to this page. We are the signal cross reference, and here we have the next page of this drawing, and let's also dive into the hierarchy of this hierarchical block. So we dive into the next hierarchical level, and you will see this here. And here we have some lamps, and when we deactivate, for example, this switch, you see this lamp is deactivated and this one is also deactivated because we have a connection via the signal cross reference from here to here, and we have also a connection into the hierarchical level from here to here. And you see when I operate this switch, the lamps are going on or off, and even in the hierarchical level I have a switch, and when I operate this switch, the connected lamp is off, and when I operate this switch, this lamp is off or on individual. So you see this will work over several pages and not only for one page. So let's go to the next example. Here we see the effect on the voltage. Once again, there is a small example. We have a power supply, a fuse, and we have some resistors. And with this stepping switch, we can change the voltage, and this is shown by this voltmeter. It's a component we have added in the E3 database with a text node showing the actual voltage. And there is another example to show the current, and there is a combined example to show current and voltage. And with this stepping switch we can change the voltage, and with this stepping switch we can change the load. We have different resistors to change the current. So let's have a closer look to this area. Now we are operating this switch, and you see the current is changing because we change the resistor, and here we can change the voltage, and now we change the voltage. It's 0.6 ampere, we have 26 volts, we have 39 volts, and we have 52 volts, and here We can also change the current, and we can set up this. So this will be also maybe a good example for education. You can use this also for training classes. So far for this live demo, and now let's go on with the slides. As we have seen the base functionality of E3.eCheck, we now have a look on the impact to the E3 database. First, we will have a look at the symbol in E3 series up to now. Next, we will see how we can add additional information to a symbol using functional units. Then we will see the minimum information we need for E3.eCheck. At the end, I will show you the additional functions for the symbol definition. Let's have a closer look to the symbols. Here we see a symbol from the user's view. The symbol has pins and a symbol graphic. The user interprets the graphic, for example, a resistor or a lamp. E3 series will see only the pins without any function. To do the checks and the calculation, we definitely need more information. To store additional data for E3.eCheck, we use functional units. Here we see a functional unit for a resistor. The type is resistor, and the value of resistance, for example, is 100 ohms, and there is also a maximum power needed, for example, 10 watts. Next example is a functional unit for a lamp. The type is load, and there is needed a resistance, a minimum voltage, a nominal voltage, and also a maximum voltage. The lamp will be active from 10 volts up to 24 volts. The symbol state is active, means symbol is yellow. Below 10 volts, the lamp will not work, symbol state is inactive. Over 24 volts, the lamp is blown, symbol shown in red means overload. Functional units are similar to simple simulation models, and they can be assigned to a symbol. Here we see the minimum information for functional units. For a voltage source, we need a nominal voltage. For a current source, we need a nominal current. For a ground symbol, we need no further information. It's the reference for the calculations. For a relay coil, we have to define the resistance, the minimum voltage, the nominal voltage, and also the maximum voltage. For a switch, there is no value we have to define, but we have some different states available. For a load, we have to define a resistance, a minimum voltage, a nominal voltage, and also a maximal voltage. For a fuse, we have to define a resistance and also a rating. And at last, for a resistor, we have to define the resistance and also the power of the resistor. We have implemented additional functions for the symbol definition. There is a new function to assign a functional unit to a symbol, and it's possible to assign graphic elements to current states. This allows to show the current state in the schematic. Here we see two examples with status inactive and status active, and for a better overview, the changes in the graphic can additionally be marked with a filled gray circle. To view the different states of a symbol already in the symbol editor, we have a new function called Simulate State. This will show the possible states of a symbol while creating the symbol. At the end, let's make a conclusion. E3.eCheck calculates a lot of parameters during the input of a drawing, but it's no simulation. The calculations are all done online. You always have actual information about current and voltage in the whole schematic. There is additional information available in the tooltips and also in the result window. Errors were shown in the graphic, and there is also an acoustic warning. When the current is more than the defined fuse duration factor, you will get a warning. This helps to recognize possible overloads. There is enhanced functionality for switches and relays. What are the advantages for the user? E3.eCheck is an ideal supplement to the already existing online checks of E3 series. E3.eCheck is fully integrated into E3 series. E3.eCheck is very easy to use. E3.eCheck can be used on existing projects. Existing databases can be used for E3.eCheck with a minimum effort. E3.eCheck helps you to optimize the wires. E3.eCheck is the ideal supplement for your design process, and E3.eCheck helps to increase your quality, and also E3.eCheck provides additional safety for your engineering process.